All right, hello, hello. Do this, we don't need that. Go. Okay, so I know we have 8 or 9 or 10 people in here. I can't remember the number off the top of my head. And I think that everyone may have already signed up for my math lab, but as a reminder, you were supposed to do it before class today, but I'm going to give you a slight extension because my math lab has been having problem after problem. It's the beginning of the semester. Even though it's the summer semester, they're having server issues. And I know I mentioned on Tuesday, I couldn't even do some things in my math lab. I couldn't set up homeworks. I still couldn't do it yesterday. It was only this morning that I finally have access to some stuff. Now, as far as I know, people were still able to enroll because I saw 8 people enroll. But if you maybe just had really bad luck, I'm going to give you until 5 p.m. today. So not sign in, but create my math lab account using the course ID and the syllabus and Canvas by 5 p.m. today, or be deleted from the course. You never existed. And that'll be the last warning. Also, one more thing about homework. There's a skills check quiz for each chapter. And you are supposed to complete them before you have access to the homework. So hopefully, yes, so here we go. So now you have things assigned. I don't think they were assigned before. So the chapter R stuff, there's no flags for that, but you'll notice chapter 1, flag, 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 flag. Now I only grade the things that say section 1.1, section 1.3, section 1.8. You'll have grades for the skills check quiz and the review of that, but they don't go for or against your grade. I will even admit you could just open the skills check quiz, you could submit it, but it's going to make your homework longer. What this does is, if there's a problem that you already understand how to handle really well, if there's 5 of them, that was weird. If there were 5 of them, and you get the 1 or 2 on the pre-check correct, then maybe you only have to do 1 or 2 of them, or maybe even not any of them at all in some instances. It just depends on the rates of things. So just be aware that you have to do these first, then these flags will go away. If you want to not really have this be integrated, then that just means you can open the quiz, close it. I need to turn my volume down because whatever noise that was about blew my eardrum out. Holy cow. All right. Where was I? So if you just turn in the quiz without doing it, then you're going to get all the questions. If you put in an effort, you might have less homework than others. So that has been integrated to this course. And again, the grades for these 2 things won't count for or against you, these 2 things. This is a review of the quiz. Yeah. And the due dates will get set up very, very shortly. But for now, we noted that, we noted that. We can go ahead and get into chapter 1. So chapter 1, and it throws me off because we have a new book with very different section titles and kind of combining stuff. And my notes still go with everything, but every now and then it's just a different title. 1.1 limits a numerical and graphical approach. And so I'm going to lump these together. This is not something I ever do again for the rest of the semester, I don't think. But honestly, these 2 sections should be one. I'm not sure why they're separate, so I like to teach them together. And I'm not saying I do everything all in the same moment. I just call this one section. And then 1.2 is algebraic limits. AIC, I can spell. And continuity. All right, so the idea of a limit, before we get into that, we need some notation. We need this, what we call approach notation. So arrow notation or approach notation. if you see something like this, x, and then an arrow, and then a 1, I don't want to do that part yet. This says, as x goes or approaches 1, as x goes to 1. That's the way that reads. But there's variations to this. You could see this as an x with an arrow and then a 1 with a little minus sign above it. And that is approaching from the left side. So this is as x goes to 1 from the left. Or if you have what looks like a plus sign as an exponent, that's as x goes to 1 from the right. Quotes. There we go. I guess I could have typed those parts out, but when you have the little drawings and then typing things, it gets a little weird. So that arrow notation is going to be critical, because we're going to see it in every single problem, basically, for the first several sections of this course. So that arrow notation is used in what we call limits. So we got notation. The limit LIM as x goes to c. That's a bad arrow. So the limit as x goes to c of f of x. This is the notation for the problem that we're going to call finding the limit. Finding a limit is seeing what a function is tending towards to, what the output is tending towards as our input is heading. So we're going to say, all right, we're going to let the x value approach 3. What happens to the y value? What is that approaching? And the idea of approaching is very important. Let me see if I can just type this out. Yes. So this states, oops, I missed my equals L. This is not nearly as difficult to do in a traditional class. So then what you'll have is you'll end up getting a number for this, maybe. So L is a number. So this says the limit as x approaches c of f of x. Again, that is read as the limit of f of x as x approaches c, or the limit as x approaches c of f of x, and it turns out to be the number L. So this states that the limit of f of x as x approaches c is the value L. C is a number, L is a number in general. This is the definition of a limit. The limit as x approaches c of f of x is equal to L. So the f of x would be a given function, or a graph maybe, an equation, a graph, a function, anything. And we want to know, all right, as you go really close to one value on the x-axis, what is it going close to on the y-axis? What is the function approaching? Now, this is the total limit. This is considering approaching from the left side and the right side, but we don't necessarily have to approach from both sides. We can approach from just the left or just the right. Let me go ahead and get some space just in case. I don't trust this too much. Okay. So the limit as x approaches c with a little minus sign that looks like an exponent of f of x is equal to L. This is the limit as we approach from the left. Left only. You don't even think about the right half of the graph. You cut it out. It doesn't exist. Or we can approach from the right, and I think that you can figure out what this would look like. You get a plus sign as your exponent instead of a minus sign. So this is the limit as we approach from the right only. Think about your number line. The negatives are on the left, the positives are on the right. The negatives are on the left, so if you have a negative as the exponent, you're coming from the left. Positives are on the right. So if your exponent's a positive, you're coming from the right. And I'm not saying we're heading towards 0. You could be. It just depends on what the number c is. All right. Limits can be finite, which means there is a number, an L, a 3, a 9, a 12, whatever. Or they can be infinite, which we often say the limit does not exist if it's plus or minus infinity. Often, and this is kind of jumping the gun a lot, but I want to go ahead and say this. Often we can simply plug in the x value into the function to get the limit, but it's not always so short or easy. All right. So this is our limit notation. This is the general limit where we consider the approach from the left and the right side. We'll have a function, and we expect a number or an infinity as the answer. And this is just the notation. You put LIM in front of it to abbreviate for limit. I've seen some people just use an L, but it's kind of abbreviating too much. Maybe your teacher's done that in the past. But sometimes you only think about the left or the right side. So if you're approaching from the left, you put a little minus as an exponent, or a plus as an exponent from the right. And let's actually get into trying to use this. So for example 1, let's find the limit as x approaches 1 of f of x if f of x is equal to 2x plus 1, and we're going to do this by using tables, table of values. So our function is 2x plus 1, and we want to find out the limit as x approaches 1. A limit is like a game of I'm not touching you between two brothers or a brother and a sister or something like that growing up. You want to get as close as possible to the thing, to the number, without actually using that number. That's why I say often we can consider just that number, but it's not always that simple. I really don't want us to focus on this too much yet. Let's focus on the idea. So imagine me in front of you, and I take my finger, and I put it about an inch from your nose, and I go, I'm not touching you, I'm not touching you. And then I'm going to put it about a half an inch from your nose, and I go, I'm not touching you still. And then I put it maybe like a quarter of an inch or a tenth of an inch, and I just keep getting closer and closer to where you can practically feel the tip of my finger on your nose, even though I'm 0.1 micro inches away or something like that. And that's kind of weird to use micro and inches together, since micro is more of a another system, but that's okay. It would just be a ratio of an inch. So I would never actually put my finger to your nose. That's the idea of a limit. You never actually get to that point. You just think about what happens as you get to that point. And the limit of me saying I'm not touching you and I'm not touching you and is you getting annoyed with me. That would be the limit. But we're going to be doing numbers and not noses and talking about noses and fingers sounds like something else. You can pick your friends and you can pick your noses, but you can't pick your friends' noses, as they say. Sorry, had to do that cheesy joke. So we want to do a table of values. And this is what we're going to set it up like. I'm going to use red for the numbers we're going to plug in. Let's do an x value of 0.9. That's a terrible looking 9. Then let's do an x value of 0.99. Then let's do an x value of 0.999. And that'll be enough. So we're going to throw these three numbers into the function and just see what happens. So 2x plus 1. I'll pull out a calculator just in the sense of keeping this simple. So each of these function values, I'll show the work for a couple of them. For these at least. Here we go. So f of, oops, black, please, thank you. F of 0.9 would be 2 times 0.9 plus 1. And that would be 2 times 0.9 plus 1. And you get 2.8. So that's 2.8. So that's what goes here. When we plugged in 0.9, we got 2.8. The f of 0.99. Well, that's 2 times 0.99 plus 1. 2 times 0.99 plus 1. And you get 2.98. And then f of 0.999 is 2 times that number. Then the plus 1. 2 times 0.999 plus 1. And you get 2.998. Now you could keep doing this if you wanted. You could plug in 0.9999 and you'd get 2 times 0.9999 plus 1. And you end up with 2.9998. And you could plug in 0.99999 and you'd probably end up with like 2.99998. I had to say it right. Now, do you have to approach 0.9 then 0.9? Do you have to do it in this exact way? No, you could do 0.9, then 0.95, then 0.98, then 0.99, then 0.995. And the point is, I'm getting closer and closer and closer to 1. We started out 1/10 away from 1, then 100th away from 1, then 1,000th away from 1, and then I showed it but didn't write it. 10,000th away from 1. And that function value, you know, when we were relatively close, it was 2.8. Then we were closer, 2.98, then 2.998, and 2.9998, and 2.9999999999998, etc. The point of the limit is, what number does it seem like this right column is approaching? So think about what number f of x is getting closer and closer to. Well, I think if you're very careful, if you think of a basic number that it's getting closer to, it's getting closer to 3. So the limit as x approaches 1, now this is not the entire problem, this is only half the problem, because 0.9, 0.99, 0.999, this is from the left of 1. So earlier we had left and right side limits. What we are currently showing is this one, because we're using numbers to the left of 1, like 0.9 and 0.99. So I have to put a little minus sign as an exponent saying we're approaching from the left of our function is equal to 3, because that's the number we seem to be getting closer and closer to. Now, is this some type of proof? Is this absolute? In fact, no, it's not. But it's good enough in a business calculus class. It's actually good enough in an introduction to calculus class as well. Now, when you start talking 400, 500 level mathematics, you get in these things called epsilon delta proofs, which we won't even touch with a stick here. So that's the left side. Let's do the right side now. So let's go with a table of values. Now we need to approach 1 from the right, so like 1.5, 1.1, 1.01, something like that. And let's just start with the 1.1. Then we'll go 1.01, then 1.001, and you could keep doing this and keep doing this if you like. I'll show the evaluations this time one more time. So f of 1.1 would be 2 times 1.1 plus 1, which is 2.2 plus 1, which is 3.2. I don't even need the calculator for that. I didn't need the calculator for any of them, but if you don't trust me, 2 times 1.1 plus 1, 3.2. Then we can do f of 1.01, which is 2 times 1.01 plus 1. That's 2.02 plus 1, which is 3.02. Then we do f of 1.001. That's 2 times 1.001 plus 1, which is 2.002 plus 1, which is 3.002. So this right here represents us approaching the function from the right side, approaching the value of 1 from the right side, that is to say, because we're using values to the right of 1. I didn't mix and match. I only approach from the left and I only approach from the right when I'm doing these tables. So the limit of our function as we approach 1 from the right side, 3.2, 3.02, 3.002, seems to be 3. Now, in order for a limit to exist, these must match. The left and the right sides must match. The regular limit, not a one-sided limit. In order for the regular limit approaching both sides to exist, the left and right limits must match. If one of these was a 3 and the other was a 5, there's no limit. You can say the limit from the left is 3 and you can say the limit from the right is 5, but you can't just say the limits, is it 3 or 5? Which is it? And it is possible for a function to do that, especially with piecewise defined functions with what we call discontinuities, as we'll give that definition later. But we've already demonstrated that visually last time when we talked about piecewise functions in the review very quickly. So what we can say is, the conclusion of this problem is, so the limit as x approaches 1 of our particular function is 3, because those numbers matched. And if you want to write what the function is, you can say the limit as x approaches 1 of, and it was 2x plus 1, you can say that equals 3. You can use the function notation or you can actually write in the function. Both of those are acceptable. So that's how we can do a limit with a table of values. You have to show the work for a couple of numbers from the left, getting closer and closer to your value, a couple of numbers from the right, getting closer and closer to your value. And then the limit only exists if those answers match. Is it tedious? Yes. Is it slightly time consuming? Yes. Is it a necessary evil? Sometimes. Are there quicker ways to do this? Most of the time, absolutely. So this was using tables, but we also could have done it by graphing. We could have also done this by graphing. So I'll pull out a TI-83 for the next problem. Let me pause my screen for a second so I can get that. Okay. I don't know why I paused the screen for that. That was silly. I didn't need to do that. There's one thing you have to pause for, and it wasn't that. All right, I gotta remember that. So the next example we'll use our TI-83 for. Now, you are coming from pre-calculus, so if you got a pre-calc course that was taught in the right amount of time, hopefully you learned how to graph rational functions in there. But still, it's not a skill I'm gonna heavily rely on in here for y'all. So we'll just pull up the calculator for it. So example 2. Find the limit as x approaches, or as x goes to -2 for the function x plus 2 over x squared minus 4 by graphing. This would be super tedious to do a table of values and actually show all the arithmetic and algebra. So we're just going to do this by graphing. So let's find the limit as x approaches -2 of this function. This is our function x plus 2 over x squared minus 4. So by graphing, so let's just pull out a graphing calculator, go to our y equals screen. This is a polynomial with multiple terms in the top and bottom, so parentheses are necessary. X plus 2. Close it, divided by other parentheses. X squared minus 4. And I'm going to go ahead and spoil this. We're going to come back to this problem later. And then I can hit graph. And it kind of looks like a heartbeat, kind of looks like an impulse electrical signal, but this represents a vertical asymptote. These old calculators aren't just going to automatically draw the dotted line for your vertical asymptote. It ends up just kind of looking like this. But this function from the left of that number is going down forever to negative infinity. But then if you approach from the right, you'd be going up forever to positive infinity from the right side. So it's kind of a weird behaving function right there, which typically rationals have that kind of feature. But that's a positive 2, and we're not interested in positive 2, we're interested in negative 2. So the limit depends on where you are. I could say, what's the limit as you approach 5? And we'd be interested in somewhere over here. I could say, what's the limit as you approach 0? And we're interested over here. I could say, what's the limit as you approach positive 2? And we would be interested in this weird negative infinity, positive infinity issue, which, spoiler alerts, that limit does not exist because positive infinity and negative infinity aren't the same number. But we're interested over here at negative 2. So I can hit my trace button, and then I can type in numbers. So I can type 0, and we can see if we were to plug that in, we get -0.5, negative 0.5. We can see if I plugged in positive 2, it says y equals blank, because that's an asymptote there. That's a vertical asymptote. You can't plug 2 in because it makes the bottom 0, and you're not allowed to divide by 0. It's one of the biggest issues we come across in math. You can't divide by 0. Unless you're like a quantum computer or something, and I'm not going to get into those subtle details because I don't even know most of them. So we're interested in -2. Now, if I just type -2, check this out. I said earlier that sometimes you just need to evaluate the function. But if I type -2, it's blank. You might say, well, why is that? It doesn't have that asymptote over here at -2. It looks like it's just going along. Well, if you plug -2 in the bottom, -2 squared is positive 4, and 4 minus 4 is 0. It makes the bottom 0, so that number can't be in the domain. But it's not an asymptote because that also makes the top 0. It's a common factor, and common factors that cancel are wholes and not asymptotes. So that was an important issue from pre-calc 1. It's an important issue that's covered in the review material. So if you're rusty with that, I just said it all, but you can practice with that in the review material. All right, so the point by graphing, we're going to do the same thing as up here. Let's not just plug in -2. Let's do something like, negative 2.1, negative 2.01, negative 2.001, and negative 2. Or negative 1.9, et cetera, et cetera. So let's hit trace again, excuse me, and let's approach from the left. So to the left of -2 would be like negative 2.1. So if we plug in negative 2.1, we get negative 0.243. So negative 0.243, I'm just going to write these down. I'm still going to write the table of values. And then we'll do negative 2.01 and negative 2.001. And let me do this. Come on. So I can see my calculator and that at the same time. Stop that, you silly computer program. Why is it cutting that side off? Ay, ay, ay. Oh my Lord. I don't know why this is giving me such a headache. there. Okay. So we typed in the negative 2.1 and we got negative 0.244. Negative 0.244. Okay. So let's hit negative 2.01. And we get negative 0.249. And then if we do negative 2.001, we get negative 0.2499. And we could do this again if we wanted to. We could go negative 2.0001. We get negative 2.499938. So it seems like we're getting closer and closer to negative 0.25, which would also be known as negative a fourth. So this is the left-sided limit. This is from the left. And it seems like the limit as x approaches negative 2 from the left, I'm just going to write a f of x here, is negative 0.25. If we do it from the right, though, so we'd need something like negative 1.9, negative 1.99, negative 1.999. So negative 1.9. And that's negative 0.256. If we do negative 1.99, negative 1.99, this thing doesn't like quick double clicks, negative 0.251, 6 there, because I got to round the 0, 6 up to a 1, and then negative 1.999, we get negative 0.250. So 0.256, 0.251, 0.250. And if you don't trust this, you can go negative 1.999999999. And it even basically gets to that number of 0.25 because it even rounds it for me. So that's kind of weird because it says when I plug in negative 2, I get negative 0.25. This is just a display round. It did not actually plug in negative 2. It plugged in negative 1 point and then however many nines. That's just a display issue. So it seems from the right, and I forgot no, I didn't forget the minus sign. The limit as x approaches negative 2 from the right of our function also appears to be negative 0.25. So that says, since those numbers match, the limit as x approaches negative 2 from either side of x plus 2 over x squared minus 4 is negative a quarter, 0.25. Which is super interesting because when you actually type in negative 2, that output is blank because it's undefined because there is a hole. So this is one of the first fascinating ideas of calculus. So note, f of negative 2 is undefined. There's a hole there because it makes top and bottom 0. Common factor, which would cancel out. If you simplified this, you could factor the bottom as x plus 2 times x minus 2 and then cancel it, and you'd only have 1 over x minus 2. But you have to use the original function when you're talking about restrictions and things like that. You can't reduce things because then you're missing information. So note that the function value is undefined, and yet the limit exists. The number that we're approaching is different from the actual number we get, and this can be seen in all sorts of applications. So let me show you a couple pictures of some weirdness. And I'm just going to stick these in the first quadrant to make it easy. Let's have this graph right here. Hold on, sorry, I got something happening here. I just dropped something. Give me a second. Okay. So let's have this be our function, basically, some random curve. But let's put a hole here, and let's actually have its function value up here. And I'll call this value C, since we used C earlier. It can be any number. And then you have a height here of A and a height here of B. Now I'm going to do a couple variations of this function. So this one's got something weird going on. This one does not. It just has a normal point there. That's a height of A. And then let's have the same picture here. Oops, wrong mark, wrong mark. Have our hole here. Have the function value up here. This will still be our C, our A, and our B. But I also want to put a D over here with the exact same height as A. So this point right here has the exact same height. It doesn't look perfect because I'm not a great artist. I just put the D a little too far to the right, that's all. Here we go. Let's do this point here, and then that'll make the D here. And I know the D shouldn't come before a C. That's not the point of this. The first one, we're going to go, just make a few notes. F of C is equal to B. That's a terrible looking C. F of C is equal to B. Because there's a hole here and it's shaded up here. So this is like a piecewise defined function. The function is this curve for everything except at that number, but then at that number it's up here. So the function value is the shaded point at a height of B, but the limit as you approach the same x value of the function is A, because as you approach this value from the left, you're heading to that point. As you approach from the right, you're heading to that point. This random jump cannot be seen when you're going, 0.9, 0.99, 0.999, 0.99999, or 1.1, 1.01, 1.0001. So the limit and the function value are completely different for that one. For this middle one, oops, back to black. F of C is A because it doesn't have that discontinuity jump, and the limit as x approaches C of the function is A. Because when you approach from the left, when you approach from the right, you're still heading towards that. Now this one over here, I'm going to do F of D. Well, F of D has a height of A, so that's there. But I'm not using C, I'm using D. And then the limit as x approaches D of f of x. So I would say most often than not, if you've got these weird little discontinuities, they're usually more interested in that section, but they don't have to be. And that's exactly what's going on in this third case. I'm interested over here. There's something weird going on over here, but that doesn't matter for the limit because we're interested in what happens from over here. Well, the height of the function is A, and as you approach from the left, as you approach from the right, it's also A. It had nothing to do with this weird section over here. I didn't even need to know that for that problem. Whereas with the first one, I did. Let's do another one of these. Let's do another piecewise defined function. Let's say we had a little curve and an open circle here, and then a closed circle here, and it was a line. And let's call this point C, and these heights A and B again. So let's only focus on the C. So for this one, f of C is equal to, well, is it A or B? Well, it takes the shaded one, it takes the B. Now, if we come from the left, we're approaching this height right here at A. So the limit as x approaches C from the left of the function is the A height. As we go left, we're approaching A. As we go from the left, that is to say, we're approaching that. But as we come from the right, we're on the line part instead of the curve, and we're approaching a height of B. So the limit of f of x as you approach C from the right, this would be the B. These don't match, so the limit as x approaches C of the function does not exist. D and E means does not exist because they're different values. We're approaching 7 from the left and 10 from the right, something like that. Excuse me. Let me mute for a second. So in calculus, very often we're interested in what we're approaching and not what the actual value is. It's great when they're the same thing, but they don't have to be the same thing. I am so sorry. Okay. So this is the graphical approach. This is the table of values approach, which are really one and the same. What about going back to the basic idea of often we can simply plug in the x value into the function to get the limit, but it's not always short or easy, and it's not always even completable. So let's go back to this problem, the 2x plus 1. So let's do the algebra version. For example 1, can we simply plug in the x value to get the limit? So that was, the limit is we are approaching 1, I believe, right? Yes. So we had the limit as x approaches 1, the function 2x plus 1. Well, let's just plug it in. And we get 2 times 1, I'll show that, plus 1, which is 2 plus 1, and that's 3. Which was the limit. So here's a question. If you can just plug in the number and get the limit, why wouldn't you do that? Why would you want to do this graphical approach? Why would you want to do this table of values approach? Why would you want to do all this extra work if you can just plug it in? Well, because this says often you can. It doesn't say you always can. When you have functions that have this type of behavior, maybe a discontinuity where we're interested in, or maybe an asymptote like we saw on that graph, or maybe a hole like we have on this graph, or this graph, or the one we saw earlier, maybe that's an issue. So what the takeaway here is, what you can do is just try plugging the x value in and see what you get. If it's a normal function, i.e. not piecewise, if you get a value, it is generally the limit. But often functions are ill-behaved at the value we are approaching. So it worked for example 1 pretty well. If you just plug in -2 into this one right here, the x plus 2 over x squared minus 4, the top, -2 plus 2 is 0. The bottom, -2 squared is 4. 4 minus 4 is 0. And you get 0 over 0, which is known as the indeterminate form. It's both infinity and negative infinity at the same time, or one or the other. It can vary quite wildly depending on the degrees of the top and the bottom, and a few other things as well. Multiplicities of zeros, lots of details. But just plugging -2 in here, it doesn't quite work. We'll come back to that problem in a little bit. For now, let's try some ones that may or may not work. Example 3. 3, that's an ugly 3. Find by evaluating if possible. So for A, we're going to do the limit as x approaches 5 for the function x squared minus 7. So what I like to do is I like to say, okay, well, let me just plug the 5 in and see what I get. So plug it in. We get 5 squared minus 7, which is 25 minus 7, which is 18. So because I got a value, that's probably right. And if you don't trust it, let's just do the graphing approach really quickly for this. Let me hide that because I'm going to use it again later, I think. And just put x squared minus 7 here. So this is the graph of x squared minus 7, something every single one of you should be capable of doing by hand because we taught you that in pre-calc 1. If you're rusty, practice. All review material is, or all prereq material is necessary. I want to say all, but most. So if we just hit trace and 5, hey, there's a y value. That's a great sign. It's at 18, which I can't see, so I'm going to change the window. I'm just going to make the y maximum 20 instead of 18. That way I can actually see this. So trace, type in 5, and it's right here. And visually it looks like as you're approaching from the left, that's where you're going. As you're approaching from the right, that's where you're going. But let's just try a couple numbers. 4.9, 17.01. Well, that's close to 18. Let's get closer. 4.99, 17.9. That's close to 18. You couldn't tell it was going to be 18 with 4.9, but now you might have an idea. 4.999. 17.99, yeah, that's probably 18. Let's try from the right, 5.1. Yeah, 19, it's off by 1, but let's get closer, 5.01. Okay, I'm feeling a little more confident, 5.001. Yep, it's definitely going to be 18. So we are able to skip all that extra graphing analysis type of situation. This looks like an S, let me make sure, 5. All right, so let's try another one then. Maybe it always works that nicely, right? maybe not. The limit as x approaches 5 for x plus 3 over x plus 5. Now you might say, oh, this one's not going to exist because the bottom is going to be 0. Now if that was a -5 here, then you'd be right, but that's not what's happening. So let's plug it in. The 5 again, same number this time. It doesn't have to be, that's just a coincidence. So that would be red, 5 in the top, 5 in the bottom, plus the 3, plus the 5. 5 plus 3 is 8. 5 plus 5 is 10. 8/10 reduces to 4/5 though. And because I got a value, that's probably right. If you want to confirm it with the graph, parentheses x plus 3 divided by parentheses x plus 5. Graph. Oh, I thought I covered the second one. That's all right, whatever. I only need to see one of these. And you can see over here at +5, and you can use the left and right arrows to get closer. We're in the 0.8 ballpark, so that's a pretty good sign. If you do 5.00001, let's just go ahead and get really close. 0.8 and then a bunch of zeros and a 2. Well, that's ridiculously close to 4/5. So that's a good sign that it works from the right. How about from the left? How about 4.999? 0.79998. Yeah, that's pretty close to 0.8, which is 4/5. C. The limit as x approaches, let's do a different number this time, 9. And we'll have the square root of 3x minus 1. So let's just try plugging it in. And we get the square root of 3 times 9 minus 1. 3 times 9 is 27. 27 minus 1 is 26. So we get the square root of 26, which, yes, it has a decimal approximation that I don't care about. I mean, we got a number, so that seems pretty good, right? And again, you can confirm with your graph. Square root, 3x minus 1. Close the parentheses. Let's go back to our standard window. So there's our square root function. No surprises. We showed you that basic shape last class again. And let's just type in 9. Oops, got to hit trace first. And we get 5.09, which guess what is square root of 26. Now you're not going to be able to tell that graphically because it's an irrational number. So you would definitely have to do this one algebraically, because if you type in, let's say 9.0001, I'm going to guess that some people are going to think they're approaching 5 or 5.1. But if you do 8.999, 5.09 as well, it's not like one of them was 5.09 and the other was 5.1 something. So that's a sign that it's a weirder number when the left and the right numbers aren't kind of sandwiching another value. So that would say, I'm sorry. That would say you should probably go to the algebra, and that's because it's a square root function, and square root functions have very goofy outputs. Now I need to point out something. This function starts right here at an x value of 1/3. How do I know it's 1/3? Because if you set the inside equal to 0, if you find the domain of this square root, you set the inside bigger than 0. And that's all the x values you can use. You can't use anything less than 1/3. If I type, I do trace 1 divided by 3, you get an output of 0. If you plug that in, 3 times 1/3 is 1, 1 minus 1 is 0. So this is the very first point where the graph starts in terms of left and right. If I had tried to find this limit, it doesn't exist. You cannot find the limit at 1/3 or anything to the left of it. Because check this out, if you're approaching from the left, the function doesn't exist. There is no left-sided limit, because how can you approach something that's not here? You can approach from the right, and approaching from the right, you are certainly hitting a y value of 0. So the right-sided limit is going to 0, but the left-sided limit, you don't know where you're coming from. Are you up here? Are you up here? Are you up here? You're nowhere. So there is no left-sided limit. So be careful with square root functions. That's what I'm kind of getting to here. Where's my mouse? Be careful with special classes of functions like square roots. They do not have limits at the boundary where the function starts or where the function doesn't exist. So for square root of 3x minus 1, if I ask you what the limit as you approach -9 is, You can't plug -9 into this because 3 times -9 is -27, -1 is -28, and the square root of -28 is an imaginary number. Now, we can certainly do a billion things with imaginary numbers. They're not even imaginary. They exist. The concept that's imaginary is their x-intercepts. That's what doesn't exist. But imaginary numbers are very much an important aspect of the real world. Science, engineering, physics, chemistry, biology, all sorts of good stuff. So again, the point of this is if I'd done the limit as x approaches -9, that graph doesn't even exist. You can't plug it in because there's imaginary numbers. If I asked you what the limit as you approach 0 of that is, it would also not exist because the left side and the right side don't match. So the limit as x approaches, I'm sorry, not 0, 1/3 of the square root of 3x minus 1 does not exist, since the left side limit does not exist. The right side limit is 0. As we showed, the right-sided limit is 0, but the left-side limit doesn't exist because you can't approach to the left of something if there is no left. There is no spoon. Outdated movie references, I apologize. Although I guess a fourth one's coming out. Maybe. Who knows what's happening with entertainment, right? And if you don't know what I'm talking about, just Google "there is no spoon." I'm sure you'll figure it out really quickly. Okay, so we had some examples where we were able just to plug in the numbers and get the limit, and I didn't box up the last one. Let's go back to this one, example 2. We're going to do example 2 again, but instead of graphing, we're going to do it algebraically. And we're going to call it example 4. Find the limit as x approaches -2, and our function is x plus 2 over x squared minus 4. So again, and we're going to do this algebraically. So try plugging it in. And we get -2 plus 2 in the top over -2 squared minus 4 in the bottom. Please make sure you know how to square negatives in this course. Simple arithmetic mistakes are unacceptable at this level. -2 plus 2 is 0. -2 squared is +4. 4 minus 4 is 0. And this number doesn't exist. 0 divided by 0, we can't divide by 0. So this is an indeterminate form. So when this happens, it doesn't say that you can't do it this way. Oh no. I'm just gonna have to go down here. I'll write it here. When this happens, I can't type in this spot, unfortunately, but I want it on the same page. When this happens, try simplifying the original function. Often simplifying means to reduce. So let's go back to the original problem. The limit as x approaches -2 for x plus 2 over x minus 2. That's not right. Sorry, I'm a step ahead in my head. X squared minus 4. So this would be the limit. And yes, you do have to keep writing this every time in your work. It's tedious. of x plus 2 over, well, the bottom's factorable. So factoring is often helpful, and that's a difference of squares. I've already told you that you have to be kings and queens of factoring. I gave you some worksheets and website links and everything in Canvas to help you with that if you're rusty. There's always Purple Math and Khan Academy. There's some practice problems and your review homework. But again, you're supposed to know this. So this becomes x plus 2 times x minus 2. That formula is a squared minus b squared equals a plus b times a minus b. And when you do this, you end up with matching factors top and bottom. And this is very often what makes this indeterminate form become, well, determinate. So now what we have is the limit as x approaches -2. With the top gone, that's now just a 1 over. The bottom is now just an x minus 2. And when you see something drastically change like this, now try plugging in again. So this would be equal to 1 over -2 minus 2, which is -1/4. And seeing this negative, I realized that I forgot to write my negative earlier. No, I didn't. I lied. I thought I made a mistake and I didn't. Look at that though. So the limit as x approaches -2 for x plus 2 over x squared minus 4 is equal to -1/4, the same answer we got graphically earlier. But you can't do it right out of the gate because there's a common factor top and bottom that when we plug the number into that common factor, it makes both of them 0 and it gives you something that's indeterminate. Now, if it's just 0 in the bottom, you can potentially say the limit's infinity or negative infinity. It's when you get this that you absolutely had to have reduced it to then get the real answer if it exists. So be on the lookout for that. And that's one of my favorite types of problems to give because it makes sure that you know how to factor. It makes sure that you're paying attention to processes and it makes sure that you're practicing. So let's do a couple more of these. How are we on time? 12:03. B. The limit as x approaches 6 for x squared minus 12x plus 36 over x squared minus 36. So I'm going to go ahead and tell you if you plug in 6 into this problem, I'm not going to show the work. The top and the bottom will both be 0. In the bottom, 6 squared is 36. 36 minus 36 is 0. In the top, 6 squared is 36. That 36 at the end is going to add and make it 72. 12 times 6 is 72, so that's a -72. You have +72 and -72, and they cancel, you get 0 over 0. So you must simplify first. If you're trying to plug in the 6 because it would make the top and bottom 0. Now here's the thing, if I said what's the limit as you approach 5, you could plug it in now. If I said what's the limit as you approach 12, you could plug it in now. If I said what's the limit as you approach 0, you could plug it in now. It's only when that number being plugged in makes the top and bottom 0 that you have to try and simplify it first. Because I'm not guaranteeing that this simplifying, canceling thing always happens. I could change this to a 5, it's a completely different problem. I can change this to a -2 million, completely different problem. So we go equals limit as x approaches 6. So x squared minus 12x plus 36. We're trying to find a pair of numbers that multiplies as 36 but adds to 12. Well, 6 and 6. So we go x, 6, x, 6. But these 6's have to multiply to +36 and combine to a -12, so they both need to be negative. If you are not great with your arithmetic with signed numbers, you need to spend 20 hours working on that before next class. Because that's important for factoring, and factoring is never going away in this class. The bottom is another difference of squares, x squared minus 36. That would become x plus 6 times x minus 6. The top and bottom are not the exact same thing. They're close, but one of the signs is different. Now, when you do this, you see that there's a pair of x minus 6's that cancel. There's a top and a bottom. You can't cancel the rest, though, because that's a minus and a plus. They're very close, but you can't cancel that. So this gives us the limit as x approaches 6 of x minus 6 over x plus 6. Now, you might be saying, well, I still see all these 6's. This isn't going to work. It makes the top 0. That's fine. As long as it doesn't make the top and bottom 0. That's when it's not fine. So now we'll plug in. So we'll do 6 minus 6. And when you plug it in, that's when you no longer write limit. It's only when you plug in the number that you no longer have to write the limit part. So 6 minus 6 in the top is 0. 6 plus 6 in the bottom is 12. And 0 divided by 12 is 0. So that should be the answer. If you don't trust it, calculator for that quick two-sided approach. Parentheses, x squared minus 12x plus 36, close it, divided by parentheses, x squared minus 36, double check everything, looks good. So here's that 6, if I hit trace, let's do like 6.0001. That E says this is in scientific notation with the decimal going left 6 times. That's 0.000008. That's pretty much 0. If I were to plug in 5.99, again, 0.0008, negative. So that's also very close to 0, one on negative, one on positive. So that says it should be 0. Now, if I actually type in 0, look at this. I'm sorry, I'm not supposed to type in 0, I type in 6. It's undefined. It is undefined at the point that we're supposed to be approaching because it's another hole. It's a hole because of the cancel factors. But even though there's a hole there, even though the function value doesn't exist, it does have a limit. We are approaching the same number from the left and the right. This is something that happens a lot of the times in the real world. So let's say you have a virus that has spread amongst the population. And eventually it has to infect everybody possible, or at least, it has to hit everybody possible, whether they get infection or they're immune. So let's just say there's a flat 300 million people in America. There's more, but let's say there's 300 million people in America. As almost all the population gets affected by this, whether in a very negative manner or a slightly negative manner, or not really any effect at all, as you interact with it, we get closer and closer and closer to a total count of 3 million. But it's really unlikely that every single person absolutely would get interacted with, because we have people that live in caves and they'll stay in there for 1 year, 5 years, or people that live in the forest, and they exist, but we'll never actually be able to hit that cap because they don't interact with the people who are spreading it. So while that number of 300 million would never be hit, we're basically saying the limit as we keep going on and on and on is that everybody will be affected. So the limit is 3 million, even though we've never really hit it. It's kind of like an asymptote. It's another idea for an asymptote. In fact, we can go to infinities, and that's basically what we're leading up to. So over here at the -6, though, that's a vertical asymptote because that factor did not cancel, so it's not a hole, it's an asymptote. All right, C. Let's do another. The limit as we approach 1 of x cubed minus 1 over x minus 1. Now that top is not a difference of squares, it's a difference of cubes. And if you plug in 1 now, 1 minus 1 is 0, 1 minus 1 is 0, top and bottom, it's indeterminate. You have to simplify first. So this will be the limit as x approaches 1. Now in that document I gave you on Canvas, this formula is up there when we talk about SOAP for the difference in sum of cubes. So your a here is x, your b is 1. So we go a, b, then a squared, a times b, x times 1 is 1x. I'll write the 1 for simplicity's sake here. And then b squared, 1 squared is 1. So again, this is the sum or difference of cubes formula. It's always a squared, b squared. Then the signs, I'll do in color. I will remind us of this. I said for cubes, you can use SOAP. Same, opposite, always positive. So the same means the first sign is the same as the original. Since this is a minus, this is a minus. The next is opposite of that, so a plus. The last is AP, always positive. This is for the sum and difference of cubes only. It has nothing to do with difference of squares. It has nothing to do with trinomials. The bottom is still just our x minus 1. And look at that. You have matching factors, top and bottom, that'll cancel. Boom, boom, gone. So this is now just the limit as x approaches 1 of x squared plus x plus 1. We're going to plug it in. So we get 1 squared plus 1 plus 1, which is 1 plus 1 plus 1, which is 3. So that's our limit. Per usual, if you don't trust it, let's do the graph. Parentheses, x cubed. Oops, why did I do that there? Minus 1 divided by parentheses, x minus 1. You okay, buddy? Sorry, my dog's got a cough. So there's our graph. It actually looks like a parabola, and that's because of the canceling. And when you cancel it, you do end up with a quadratic. But this function still has to have all the same behavior because there's a hole at positive 1 due to the canceling. You can't plug 1 into this. Yes, a polynomial, it's perfectly okay to plug 1 in, which we did, and we got the 3. But this function is ill-behaved at 1 because there's a hole because of the canceling. This is truly what we're analyzing, the fraction part. But for a limiting process, we can simplify it and then plug it in. So if I hit trace, if I type 1, it's blank because there's a hole. But if I type 1.0001, the approach, we get 3.0003. If I do 0.999, we get 2.997. So that's pretty close to 3. Our answer makes sense. It works. And if I haven't said, if you have any questions while I'm talking, please feel free to type those in the chat. I know I don't really like the mics going during class, but I'm absolutely fine with you asking questions in chat. I would never discourage questions. And you can also ask later in email. You can go to the YouTube video and say, hey, at timestamp 35 minutes, 17 seconds, what did you mean by this? If you do comment, if you need me to go to the video, please mention roughly at what time it is, so I don't spend 30 minutes hunting down the particular issue. You can also reference an example that would be able to get me there quickly too. All right, let's go back to the graphical approach, but let's do a piecewise function, and we're going to say, does the limit exist? And this is going to be the limit as x approaches 7 for f of x. And we're going to do it based on a graph, which I will paint as best of a picture as I can. Sorry for the crooked axes. It takes way too long to do this. Otherwise, we're going to have a curve kind of come up like this. We'll have a shaded closed circle for the end. We'll have an arrow on the left. And then we'll have an open circle here. And then from there, it goes up. Let's label some numbers. This x value is 7. The open circle has a height of 10. And it might not look even, but this should be a 20. So we want to know, does this limit exist? Now, I don't give you the function, and this is the function. It's this curve until you hit 7, and then it's this curve after that, where you include the left side function, but not the right side. You cannot shade both of these. You can open circle both of these, but you cannot have these both closed because then it wouldn't be a function. I'm going to do something that I can't have for just a second. If I have these both shaded, it would fail the vertical line test. That fails it. Oh man, I hate when I do this. There we go, perfect. All right, so the left-sided limit, we're coming from across this top one, so we're approaching this way until we hit 7. And as we approach it, we seem to be hitting a height of 20. So the left-sided limit, the limit as we approach 7 from the left of this graph, this function, which I did not actually give you, just the picture is what it was given, seems to be the height of 20, because this point has a height of 20. And the function does take on 20 at that. F of 7 is 20. The limit from the left is 20. But check this out. The limit as we approach from the right. So now we're going this way. We're approaching from the right, 7.2, 7.1, 7.01. We're approaching a height of 10. Now that is not the actual function value. The 20 was the actual function value. The limit from the left is 20. The limit from the right is 10. These do not match. Because they do not match, the limit as x approaches 7 of this function does not exist because it's 20 from the left and it's 10 from the right. It's as easy as that. Now in the real world, maybe you're only worried about the right-sided limit. Maybe you don't even need to worry about the left side of a function. Well, that's fine when you're talking about whatever real-world application you're dealing with, but we're introducing the basics of calculus. Now you might have a problem that only asks for the left-sided limit. You might have a problem that only asks for the right-sided limit. You might have a problem that asks for the limit. If it asks for the limit, you're worried about both sides. If we give you an algebraic function, maybe you can just plug the number in. Try that. If you get a number, it's probably true. If it's a piecewise defined function, that's another case. If it's a square root function, you have to make sure it's not the furthest left point, or furthest right if the square root's pointing left instead of right, which can be done with a reflection. Okay. So I need more. Oh no, I didn't hit enter enough. This is going to be annoying. If I insert a page, I think it's going to move all that stuff. Yes, it does. All right, in the interest of keeping this organized well, I'm just going to make a new page, a new document. Sorry for that. It's not really an issue. You see it on the screen. We don't have to approach finite numbers. We can also approach positive or negative infinity. When we do this, consider the horizontal asymptotes. Consider the. So this was a topic from Pre-Calc 1 again. Horizontal asymptotes are a height that you approach as you go left forever or as you go right forever. We've seen vertical asymptotes and we've discussed them. We've also seen horizontal asymptotes but didn't discuss them. So let me just make this a. That's not going to work actually. Yeah, we'll do this. Why did I get a pi? Oh, because I hit second first and I didn't mean to. Just going to change the problem a little bit. So this problem's got a vertical asymptote that we can clearly see right here. The horizontal asymptote is the fact that this thing is kind of flattening out as we go left or right. And that's not even very far. That's just only going to 10. We're talking about when you go to infinity. So back in Pre-Calc 1, you learned 3 basic rules for horizontal asymptotes. It's based on the degrees. Don't autocorrect me, Word. Of the top and bottom. If the degree in the top is bigger, there is no horizontal asymptote, which means no limit at x equals plus or minus infinity. If the degrees, if the degree in the bottom is bigger, the horizontal asymptote is y equals 0, which is the limit. If the degrees are the same, the horizontal asymptote is the ratio of leading coefficients, which is also the limit. So those are the 3 cases for horizontal asymptotes, which are also the 3 cases for finding limits at infinity or negative infinity. And the cool thing is they're not different. The limit at positive infinity for the functions we deal with has to be the same as the limit at negative infinity. I'm not going to say it's the same for every function, and if they're piecewise defined functions, I can't say that. I'm saying for non-piecewise, well-behaved functions, the limit at as you go left forever is the same as the limit as you go right forever. And there are algebraic reasons for that. So let's try this out. Example 6. Find this for A. Find the limit. Let's just say find the limit. For A, we're going to do the limit as x approaches infinity. It would be the same thing if I did negative infinity of 3 over x plus 2. So this is a rational function, and we're approaching positive or negative infinity. So we got to look at the degrees. For the top, the degree is 0. The degree is the exponent of the largest exponent of your x's. There are no x's, which is why it's 0. It's like having an x to the 0 next to the 3. Anything to the 0 is a 1. The degree of the bottom is 1. There's an x to the first right here. I just don't write the 1. No one writes that 1. So the bottom is bigger than the top. So your horizontal asymptote is y equals 0. So the limit as x goes to infinity or even negative infinity of 3 over x plus 2 is equal to 0. That's the answer. And if you don't trust that, let's pull up the graph. 3 divided by parentheses x plus 2. This thing flattens out really, really quickly. This thing is asymptoting really, really quickly. It's getting closer and closer to 0 without ever actually hitting it. Now, if I go to, let's just make the window. Let's make the x maximum 1,000. Now let's make the y values just go between -1 and 1. And I still can't even really see this because this is so wide. But if I hit trace, over here at almost 5,000, we're at 6.00 times 10 to the -4, which is 0.0006. And if you keep going right, if you go to a 9,999, that's 0.0003 basically. This thing is getting closer and closer to 0 as you go left or right forever. So again, we're not trying to think about just approaching right here on the x-axis. We're going right as far as we can. That's the drastic difference here of an infinite limit versus the other type of limit, which is a finite limit. B. Let's do the limit as x approaches infinity or negative infinity, doesn't matter. Let's do some weirder numbers. 34x to the 5th minus 12x to the 4th over 16x cubed minus 17x to the 5th. It doesn't matter that there's the same number of terms in the top and the bottom. That's just a coincidence. What is important is that you find the degrees. You got a fraction problem, so that's a rational. For the top, the biggest exponent I see is a 5. For the bottom, now some people will say, oh, it's the 3. It's the first one. That's it. Nope. It's the biggest one. It's actually the 5 here. That's the degree of the bottom. These are the same. So under those 3 cases, if they're the same, the horizontal asymptote is the ratio of the leading coefficients. So the horizontal asymptote is y equals the ratio of leading coefficients. Ratio means fraction. Leading coefficient means the number in front of the variable that has the biggest exponent. So we need the 34 and we need the negative 17. Don't forget that sign there, the 34 and the negative 17. Which is y equals -2. So therefore, the limit as x approaches infinity of this goofy function is equal to 2. So maybe this function is dictating the billions of people that are expected to get a certain virus. Again, that's not what I'm saying this is. It's not. Just saying maybe it was. So we would probably never actually hit 2 billion people, because the only time we'd hit 2 billion is at infinity, at the eventual number that never actually happens. But within a reasonable amount of time, we would be really, really, really close to that number. We might be at like 1.99 billion or 1.98 billion or 1.97 billion. So we'd be getting closer and closer to that, 1,000 years from now, 10,000 years from now, 100,000 years from now. But in the short term, in just 2 or 3 years, we would get really close to that quicker than you'd imagine. Let's do one more. C, the limit as x approaches infinity. And again, all of these problems are the exact same if it's at negative infinity. And let's go with 10x to the 8th plus 7x to the 3rd minus 3 over 4x minus 5. So the degree of the top is 8. The degree of the bottom is 1. The top degree is bigger than the bottom, which under those cases is the third one, or the second one. No, I'm sorry, the first one. The third one that we haven't used. We've seen the first 2 types. This is the third type, which was the first one we wrote. If the degree in the top is bigger, there is no horizontal asymptote. So there is no horizontal asymptote. So the limit does not exist. D and E does not exist. This thing goes to infinity or negative infinity. If you don't believe me, how many times have I said that today? And the point of me teaching you is so that you don't have to keep not believing me and going back to a graphing calculator. You just do it analytically. 10x to the 8th plus 7x to the 3rd minus 3, close, divided by parentheses, 4x minus 5. Zoom 6. That's a standard zoom. And look at this thing. It doesn't seem to be flattening out in this window. Maybe we're just not in a good window, so let's zoom out. And again, you don't really see this thing flat anywhere. And if you trace it, look, by the time we hit 1.7, we're at 407. 2.5, we're at 3,485. And that's because this top is going to get bigger way, way, way quicker because it's got an x to the 8th and an x to the 3rd. The bottom's only got a linear term. The bigger the exponent, the more it grows. So what happens as we go left or right forever? It's only the leading terms that dictate what happens. As you go to infinity or negative infinity, the leading term basically takes over everything. It's not exactly that, but that leading term is going to be so big in comparison to this x to the 3rd term, in comparison to this 3 term, that you might as well just say, hey, it's pretty much this, which is what a limiting process is doing. So basically, you only look at the leading terms. So again, these infinite limits basically only look, limits, only look at the leading terms of polynomials. So it's kind of like, and I'm gonna do this in red just to show you kind of another way to think about this. It's like if with C, this thing is approximately, when you get near infinity, 10x to the 8th over 4x when close to plus or minus infinity. But this 10x to the 8th over 4x reduces to 5 over 2 and an x to the 7th, or 5 halves x to the 7th. And if you plug infinity into x to the 7th, it's infinity. Whereas with B, when you take that infinite limit, you're only looking at the leading terms. You're looking at the first term in the top and the second term in the bottom. So it becomes 34x to the 5th minus 12x to the 4th. Why did I do the minus part? 35x to the 4th over negative 17x to the 5th, which gives us a negative 2 because all the x to the 5th cancels, and that makes a 2. Again, this thing goes to infinity if you plug infinity in, but negative 2 is negative 2. That's why this was the limit. If you do it with A, we had 3 over x plus 2. It just goes to approximately 3 over x. And if you plug infinity, if you think about plugging infinity into the bottom, you've got 3 divided by infinity. 3 divided by the biggest number in the world is the smallest number in the world, 0. If you don't believe me, take 3 and divide it by 1,000, then divide it by 10,000, then divide it by 1,000,000, then 1,000,000,000. Three divided by 1,000. Small number. Sorry, that was 10. This thing hates multiple clicks. 3 divided by 1,000. Smaller. 3 divided by 1,000,000. Smaller. 0.00003. So as we get to dividing by infinity, this thing just goes to 0. That's the rationalization behind the horizontal asymptote rules, is that the leading terms take over, and then you can actually just ignore them. You don't even need the rules. You can do it like I've done in this red ink. Just imagine yourself only looking at the leading terms, reducing it, and then plugging in infinity. X to the 7th, x to the 6th, x is going to go to infinity. If you have a number, if the x is in the bottom, that's going to turn into 0. If there's no x's, then the answer is the number you have. And that's all there is. All right. Continuity. If a limit exists at a point, it is continuous at that point if and only if, it's a mathematician's favorite phrase, the function value matches the limit. if a limit exists at a point, then it's continuous, but only if the limit and the function value match. Now we've seen a couple of cases of this that we're kind of describing here. So let's drop some pictures. And again, just sticking in quadrant 1 for the sake of sanity. Going back to this. And we'll have this point right here, C. Then we'll do the same basic shape. But we'll have a hole here. And it's there. Let's put the arrows in all these bad boys. And here we'll have an open circle, and here we'll have a closed circle. Not that it matters which is which. This will be our C. So we're going to say which of these is continuous at x equals C. Well, the first one, this point right here, if you wanted to shade it in, you can. That's the function value. This height, let's say the function values are, I don't know, let's go with D this time. So here we have a D, here we have an E, and a D, and an E. So for the first one, and let's call these capital A, capital B, and capital C. A, the limit from the left is D, the limit from the right is D, and the function value is D. So A is continuous. Because the limit from the left matches the limit from the right, meaning that it has a limit, and the function value is there. The second one, which I'm calling B, is not. Because the limit from the left is the height of D, the limit from the right is the height of D, so the limit does exist. But the function value is up here, not the same thing as the height. So that's because the limit as x approaches C of f of x is not equal to f of C. C is not continuous here because, first of all, the limit doesn't even exist. The left side and the right sided limits do not match. There's a lot of different cases for continuity at a point. Now, you can also talk about a function being continuous everywhere instead of just at a single point. So, let's just put some numbers in here from 0 to 10. So this thing is continuous at 1, it's continuous at 2, it's continuous at 3, it's continuous at 5, it's continuous at 10, it's continuous everywhere. And that's because to draw this thing, I just put my pen down and I can keep going until the far right side of it. Continuous means you can put your pen to paper and draw the whole thing without lifting it until the end. The middle image, I can put my pen to paper, but at some point I have to lift it to draw this thing up here, which makes it discontinuous. The third one, I can draw the left half, but then I have to lift my pen and put it up here to continue the right part. So that's what it means to be discontinuous. You have to lift your pen or pencil or marker or whatever off your paper, board, or tablet in order to draw it. We can talk about continuity as a whole, as a region, or as a finite point. All right. Example 7. Sorry. Let me go back to black. Let me make sure I've got enough enters hit so I don't goof this up again. Example 7. Let's do another limit. First, and then we'll do a continuity. I actually meant to do this one before. That's my bad. So can we just plug the 5 in? Because there's no way we can reduce this. Can we just plug it in? Well, we'd get 1 over 5 minus 5, which is 1 over 0, which is undefined. Oops, I don't mean to box that. So ... question mark. When you plug it in, you get an undefined value. And you can't reduce it, so algebraically we're stuck. So what you need to do is go to the back to the idea of a left side and a right side approach. And let me just pull out the calculator for that. And I'll say use a left right approach instead. As I said, you can't always just plug the number in. It doesn't always work. 1 divided by x minus 5. 6. So 5, we see that asymptote. We see that vertical asymptote, which I have not put us on top of yet. This is the first time. The other times it's been at holes. So if you put type 5, oops, you got to hit trace first. 5, it's blank, and that's because there's that vertical asymptote. So let's try 5.01. And we're at 100, maybe 5.001. And we're at 1,000. How about 5.0001? And we're at 10,000. So 5.00001 would be 100,000. You get the idea. So the right-sided limit, we're going up. These are positive numbers. 1,000, 10,000, a million, a billion, a trillion. We're going to positive infinity. So this is the right-sided limit. I'm doing this in a backwards order, not that it matters. So the limit as x approaches 5 from the right of this function is equal to infinity. How about the left-sided limit as we approach 5 from the left for this function 1 over x minus 5? So how about 4.9? Well, we're at negative 10, or is that negative 100? I can't tell because of that little blip there. How about 4.99? We're at negative 100, so the other one was negative 10, and that makes sense. About 4.999, we're at negative 1,000. 4.9999, we're at negative 10,000. So we're still approaching the same number in absolute, but we're going down instead of up. So this one's going towards negative infinity. It's going down forever. You can even see that if you look carefully. From the left, we're going down, 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 down. Then we magically hit the asymptote, which we're not really supposed to touch. And the second we cross over it, we're up here at the top, and we're going down, down, down again. But if you think about yourself approaching from the right, we're heading up to infinity. So the left-sided limit's negative infinity, the right-sided limit's positive infinity. So the limit, since they don't match, the limit as x approaches 5 for 1 over x minus 5 does not exist. Now I need to make a special note here. This is a special important note. If these had both been positive, or let's say had both been the same infinity, I don't want to phrase it any other way. If they were both positive infinity or they were both negative infinity, some people will say that the limit exists, and they'll say it's that particular infinity. Some, however, say the limit does not exist because infinity, whether positive or negative, doesn't exist. Find out which MyMathLab does. You'll be able to find that out by doing an example. If you get it wrong, then try the other way. So if you find the left and the right limit is both positive infinity and you try and type in infinity and it says you're wrong, go back and try and do does not exist and it should mark it right. And the reason I'm telling y'all is because I use 3 or 4 different, I wonder if y'all heard that. My dog hacking. Distractions. Because different teachers, different textbooks have different ideas of whether you should say D and E or infinity or negative infinity if they match. I can't definitively tell you which one it is all the time because I use 4 different math programs and I can't remember which is which. I'm still kind of used to WebAssign because that was what we were using the last time I taught this class. And like I said, it'll be a really quick check. So make sure you figure out which one MyMathLab does in the homework. That way, when you get to the testing, you'll know which it is. And I will check out MyMathLab and remind myself which one it is. That way, nobody screws it up for a test and loses points over something they shouldn't have lost it. Me personally, I prefer saying that the limit's infinity or the limit's negative infinity because that is a unique answer. It's an A or a B. But some people just like to say, well, neither of those numbers exist, so let's say it doesn't exist. But the problem is there's still times where it going to the top or going to the bottom matters. So saying that, giving it distinction can be helpful. So again, kind of a special set of notes. All right, and last example for the day, I think. I think we'll call it here if we have a few extra minutes. I don't want to start a new section with 5 or 10 minutes. And let's actually get to the continuity stuff. A, find the limit as x approaches 10 for f of x. And I'll put that down in a minute. And then for B, is it continuous at x equals 10? And our function is going to be piecewise defined. And it's going to be x plus 7 and 2x minus 3. The top one will be for x is bigger than or equal to 10. Bottom one will be for x is less than 10. So because the top one is only true for the right side, the bottom is only true for the left side, what you'll do is for the limit is plug 10 into the top to get the right-hand side limit. That's what RHS means. And then you'll plug it into the bottom to get the left-hand side limit. So for the top, f of 10 is 10 plus 7, which is 17. So the limit, now that's for numbers bigger than or equal to 10, so that's coming from the right. It says x goes to 10 from the right of our function is equal to 17. For the bottom, f of 10, and I'm going to put a little asterisk next to that because you're technically not supposed to plug the 10 in here, but we talk about this in pre-calc 1, how you can do it just to see things like continuity, whether you have open and closed circles or it just keeps moving. So that would be 2 times 10 minus 3, which is 20 minus 3, which is also 17. So the limit as x approaches 10 from the left is also 17. So the limit exists. So the limit as x approaches 10 of this function is 17. So that's the answer to A. For part B, we ask, is it continuous? Things are only continuous if the limit matches the actual function value. So we have to find f of 10, which we already did. We must use the top because that was the one that had the or equal bit right there. And we already showed the math. It was 10 plus 7, which is 17, which is the limit. So it's continuous. I'm just going to abbreviate at x equals 10. It's actually continuous everywhere, but we were only interested in the 10. Okay, so let's say that the left side and the right side limits didn't match. There wouldn't be a limit, which automatically says it's not continuous. What I'd like you to do on your own, and I'm not going to do this for another one, try to do this again with this function. The same top one of x plus 7 for x is bigger than or equal to 10. And then 2x plus 3 instead of minus 3 for x is less than 10. You should find that there is no limit, which immediately says it's not continuous at that number. But I want you to show your own work for that. I'm not going to collect or anything. It would just be a good exercise for you to do. So we have finished 1.1 and 1.2. So those homeworks are due. Today's the 21st, 5/28, 29, 20 by 11:59 p.m. So I will have those due dates set up in my math lab sooner than later, hopefully today. But remember, homework is always due a week after we complete it. So if anyone has questions, I can hang back for a couple minutes, but if not, if I don't see anything in the chat in the next 30 seconds, then we'll go ahead and let you go. Don't forget that if you are not signed up for my math lab, you have to be in that by 5 p.m. today. And the course ID is Beckner, is it 77766 or is it a 5555 something? It's one of those two things. Those are my two classes. But either way, if you log into Canvas, if you load up the syllabus, thank you, someone answered, it's 55551. But that it is also in the syllabus in Canvas. All right, so I hope this was helpful. I hope we learned something. I hope we practice this in our homework as soon as possible so we can learn it and retain it. Have a good one. Email me if you have any questions, and I'll get back to you as soon as I can. Have a good holiday weekend as well. Take care.